Hello everyone, my today's presentation topic is MMIC technology, chapter 1. Before going into details of my presentation, I would like to give you a short introduction about me. This is Mehedi-Joni. Currently I am studying 4th semester in the Department of Electronic Engineering at Kwangwoon University as a master's leading PhD student. Along with that, I am working as a research assistant in Advanced Quantum Nanomaterial and Optoelectronics Laboratory. My academic supervisor is Professor Jion Lee, and my ongoing research project is transitional metal with electrocatalyst fabrication with material characterization for cost-effective green hydrogen energy generation. These are the overall outline of my MMIC presentation. Firstly, I will talk about some basic concepts of the MMIC technology. Furthermore, I will focus on background and range of MMIC technology. After that, I will discuss active and passive devices of this technology. And finally, I will conclude my presentation by talking about its application area. In this slide, I will talk about what is MMIC technology. What is the definition of MMIC? MMIC means monolithic microwave integrated circuit. What is the monolithic IC? Monolithic IC is a complete circuit or a group of circuit in a silicon pitch. Another two important things we need to know here, one is microwave, another one is MMIC structure. How we can structurize this MMIC and what is the microwave frequency? Microwave is a radio signal in frequency range 1 GHz or more, and we can structurize this MMIC with transistor and passive device on the silicon chip. And finally, what is the operating frequency of this MMIC technology? Operating frequency should be 1 GHz to over 1000 Hz for this MMIC technology. Overall, we can see here a monolithic microwave integrated circuit is a type of microchip that is designed to operate at microwave frequency, and the MMIC is widely used in communication, radar and RF biosensing systems. Before going into details of this MMIC technology, I need to include here some fundamentals of this MMIC technology. So there are three important things. One is measurement, one is simulation, one is circuit design for this MMIC technology. So in case of measurements, we need to remember how we can measure this MMIC and where we can input this data and how we can analyze this data. So hardware in loop experiment we can do here, and long range demonstration of RF links we can connect here, and beside that the circuit design, how we can design this circuit or how we can fabricate this circuit to application of this scientific concept. So we need to remember the application of the scientific concept and monolithic microwave circuit and the RF front and E bands where is 240 GHz and 300 GHz. So here is another important thing that is called a simulation. System to circuit. In the simulation part, we need to know here the system to circuit level simulation, functional analysis of this simulation, and DSP based simulation for the real-time functional verification of the system concept. So these kind of things we need to remember here for give an overview of this MMIC technology. In this slide, I will talk about the background history of this MMIC technology. In 1664, a government-sponsored program was held in Texas in the USA. The main goal of this program was to build transmit and receive module for a phase array radar antenna. Unfortunately, the result of this program was very disappointing because of lower semi-insulating properties of silicon. Furthermore, in 1664, another integrated circuit was fabricated by gallium arsenide with a 94 GHz front end and receiver. After that, an X-band amplifier was fabricated by using MOSFET on the gallium arsenide. At that time, the performance of this MMIC technology was very outstanding. Then another research program was held in 1998 for Advanced Research Project Agency for this MMIC technology. The output of this MMIC technology now has versatile range of commercial application like TV receiver, SAR, wireless communication network, and personal cellular communication. In this slide, I will talk about and discuss about the range of the MMIC technology. So before going into the details range of this MMIC technology, I would like to compare MMIC technology and hybrid MMIC technology. What is the basic difference of these two technology? So here we can see the content MMIC technology and hybrid MMIC technology. So in case of NRE cost, the MMIC technology cost is very much higher than the hybrid MMIC technology. So another thing is shape and weight. Shape and weight for the MMIC technology is small, but for the hybrid technology it is large. For the mass production, it is very much higher than the hybrid MIC technology. For the broadband service, it is relatively good, but for the broadband service, hybrid technology have some limitations. In the MMIC technology, high level integration is possible, but in the hybrid technology, it is totally impossible. And reproducibility and reliability in case of that, so we can see the MMIC technology result is very much excellent, but for the hybrid case, it is just fair. In this slide, I will talk about the another range of MMIC technology. What is the material and device? So to fabricate this device in the MMIC technology, we need to know first of all the materials, which kind of and what kind of material we can use to fabricate one kind of device for this technology. So here we know various semiconductor material with compound material are widely used in this MMIC technology, but the main important things is totally depending on the electronic and optical properties of the materials. So here we can see some of the properties of the material. So we need to remember this kind of properties and this kind of properties performance and which kind of activity they are showing in this case. So first of all, we need to know the electron mobility, the resistivity and permittivity, thermal conductivity, another upper size and upper cost and energy band gap, and furthermore the approximate production cost. So this kind of things we need to remember to fabricate one kind of device for this MMIC technology. So here I have mentioned that various semiconductor material with compound materials. For example, we can say group 3 to group 4 compound materials. For example, gallium arsenide, indium phosphide, gallium phosphide, aluminum gallium arsenide. This kind of material we can use for the fabricating. And group 4 elements and compound of 4 elements, for example silicon carbide and silicon germanium, also we can use this kind of material for this MMIC technology. In the MMIC technology, there are two kind of devices such as active devices and passive devices. In the active devices, I will discuss slide by slide gallium arsenide MOSFET and gallium arsenide HEMT, gallium nitride HEMT, group 3-4 compound HBT, silicon germanium HBT, silicon BGT, and silicon CMOS. In the previous slide, I have mentioned that some active devices in MMIC technology, but here I will focus only just gallium arsenide MOSFET and gallium arsenide HEMT active device in this technology. So in the figure 1, we can see here the gallium arsenide MOSFET configuration. So for this configuration, here are some positive materials that such kind of source and ohmic contact and gate and drain. There are some layers, for example active layer and buffer layer and N plus layer, and this kind of configuration is putted or fabricated on substrate that is called semi-insulating gallium arsenide substrate. In case of the characteristics of the gallium arsenide MOSFET, we can see the higher performance than the silicon. So why we see the higher performance than the silicon for this gallium arsenide MOSFET? Because of the higher saturated electron draft velocity and lower field mobility. This is one of the basic reason for this higher performance. Another reason could be high resistivity for the passive components, and the final and third reason would be the direct bandgap nature and lower power dissipation properties. On the other hand, we can see another figure. It is called gallium arsenide HEMT. So for this figure, we can see the same substrate insulating gallium arsenide substrate, and it is similar kind of the gallium MOSFET fabrication device. So here we can also see the source, gate and drain, and there are some layers, and there are some doped and undoped layers, and one layer is donor layer, and 2D electron gas is also available in this fabrication method. So for the characteristics of this PHEMT, we can see it is one kind of two-dimensional electron gas, and here is also high electron mobility ability. This gate length should be here lower than 12 micrometer, while we can use commonly 5 micrometer for the fabrication of this gallium arsenide HEMT. So another reason would be here lowest noise figure with the gain, and metamorphic HEMT has become highly attractive for this fabrication method. Here we will discuss another two important active device in the MMC technology. One is gallium nitride HEMT, another one is group 4-5 component HBT. For the figure number 1, we can see the configuration of the gallium nitride HEMT, and this configuration is synthesized on gallium nitride. It means here silicon impurities donate electrons, the electron accumulator in the lower potential, and another 2GE is a spontaneous aluminum gallium nitride heterostructure. The net positive charge come from the spontaneous and piezoelectric polarization between aluminum gallium nitride and gallium nitride. And in the figure 2, we can see the group 3 and 4 compound HBT. Group 3 and 4 compound HBT, this is homojunction bipolar transistor. It is a one kind of modified version of BGT, and here the important characteristics is wider bandgap of the emitter acts, and gallium arsenide HBT has 2 micrometer emitter width, and iridium phosphide, iridium gallium arsenide, or iridium aluminum arsenide and iridium gallium arsenide show the better improvements over the gallium arsenide based HBT, because there is smaller band gap. And if we see the structure of this device, then we can see the collector, base, emitter and base, and there are some layers, and gallium arsenide and aluminum gallium arsenide N plus and gallium arsenide N. So this kind of device is fabricated also semi-insulating gallium arsenide substrate. Here we will discuss the last two active device. One is silicon germanium HBT, another one is silicon BGT. For the silicon germanium HBT, we can see here silicon germanium has the lower band gap with difference lattice constant, and it has electron mobility that is 2 times faster than the silicon, because wide band gap and improved emitter injection, reduced base transition time, and higher output resistance. Therefore, silicon germanium HBT can be used in RF, transceiver and IC application. If we see the figure number 1, then here is one structure, and that is called the one common structure for the 3 types of generation of this silicon germanium HBT. In the right side of the figure number 2, we can see the silicon BGT. So in the figure 2, we can see the base, emitter, base, collector, and some oxide layer, and the P plus and N plus polysilicon layers. And in the characteristics of this silicon BGT, we can see the silicon BGT can be fabricated in frequency range up to 25 gigahertz. The emitter width would be here 0.4 micrometer, and the double poly self-aligned technique can be used to fabricate this kind of device. And gallium arsenide HBT has 2 micrometer emitter width, and side wall space technique and buried layers and selectivity here also are present, and the greatest advantage of this silicon due to the bipolar transistor circuit and the big MOS. So we can see here the silicon BGT is something similar to the previous device, but here the substrate is used, that is P substrate, means phosphorus substrate. Previously we have discussed about the MMIC technology, about the active devices, but now we will go for the passive devices in the MMIC technology. Here we have included the inductor, capacitor, resistor, transmission light, combiner and dividers, isolators and circulators, via hole, metal, air bridge and wire bonding and bond pads for these passive devices. Previously we have discussed about the active devices in the MMIC technology. Here we will go for the passive devices in the MMIC technology. So in the passive device we have included here first of all the inductor. The configuration of the inductor, we can see the figures. So figure number 1, we can see the microstrip layout and the equivalent circuit, how we will design this circuit and how can be the microstrip layout. In the right side of this slide we can see the loop inductor and the spiral inductor, and another last important thing in this equivalent circuit of the spiral inductor. So this configuration should be there in the inductor system. So in inductor we can see there are some characteristics. By depending on these characteristics we can choose an inductor. So first of all we need to remember and we need to focus on the inductance and the implementation of properties of this inductor. And another thing is microstrip inductor has a limited inductance less than 1 H, and furthermore the loop inductor has used simplicity and ARBs is connected for the rest of the circuit for the center trapping. And finally it has no reliability problem because of the combination of transmission line and ARB bridges. In this slide I will talk about passive devices in MMIC technology, for example capacitor and resistor. For capacitor we can see the figure 1, there are some diagrams for the capacitor, and the MMIC capacitor which has high capacitance per unit area. The interdigital capacitor can be used in MMIC technology. This capacitor is composed of two metal plates separated by a dielectric material, and this configuration helps to minimize the freezing effect of the field to the ground and shorts between the upper and lower capacitor plates. But we cannot use this kind of capacitor above a capacitance of 1 picofarad due to its small and resulting distributed effects. Another example is for this passive device is a resistor. The resistor are used for the feedback of the circuit, setting the bias point of the active device for isolation and termination of the power combination and couplers. This kind of resistor are used in MMIC fabrication, including thin film of lossy metal and lightly doped gallium arsenide active layers. The efficiency of this resistor as determined by the per unit length is a function of PS. Gallium arsenide based resistors are implemented by the use of FET channel and ohmic contact, which are already available in the MMIC fabrication process. If a resistor is properly designed to operate below the circuit handling limit and the critical electric field, the thermal heating should not be a problem in the resistor case. In this slide, I will talk about the passive device in MMIC technology, for example transmissional lines, isolator and circulators. In terms of transmissional line, we can say the transmissional lines and waveguide can be defined as a device used to guide energy from one point to another point. So this kind of lines consist of a set of conductor, dielectrics or combination. The conductor thickness has a minor effect on the characteristics impedance. Therefore, the typical 100 micro thickness substrate and the microstrip length width in 70 micrometer for a 50 ohm impedance value. So the transmission lines are normally separated by 2 or 3 lines widths of the minimizing the coupling. Another two important factors are for this passive device is isolator and circulators. Isolator it is the microwave signal to pass to one to another direction. It can be achieved by using different pyrites. A pyrite metal is a mount inside as the waveguide an external magnetic field. It can create external magnetic field supplied by the C-shaped permanent magnet magnetize the ferrite. Circulators the microwave signal from one port to another device to another. So here are two important passive devices like as combiners and dividers. So we can see some diagrams of these combiners and dividers. So in the combiners and dividers, we can say here the combiners are used to combine two or more transmission line into one transmission line, used to divide the microwave signal from one transmission line to two or more transmission line. Another important characteristics is microwave signal can be combined or divided by using T connection of this transmission line into another transmission line. Different types of coupler lines are shown in figure A to E. Usually power dividers are of 3 decibel type, but unequal power division ratio are also possible. So in the passive device, the biahole and metal earpiece are much more important. In case of biahole, we can see the figure number 1, the biahole, the upper level and field biahole and the ground plane, and there are one gallium arsenide substrate. So biahole are used in microelectronics to connect different metal layers in integrated circuit. It can be also used electrically connect both sides of a silicon wafer. Wafer holes or biaholes have a wide range of application like 3D packaging, micro electromechanical system, or multi-chip stacking. In case of metal air bridge, we can see the air bridge or crossovers are required for the most MMIC technology. It can fabricate by depositing a layer metal to form the bridge connect or posts. The reliability of this metal air bridge depends on many factors such as metal thickness, contact size, bridge height and width, and interconnected metal. In the last slide of passive devices for the MMIC technology, we will talk about the wire bonding and bond pads. So in case of wire bonding and bond pads, we can see the figure A, the chip 1 and chip 2, there are some bond pads and they are connected by bond wire, and the plastic capacitance are also created between the metal plates. We can see in the diagram. Here interconnection by the wire bonding is necessary between the MMICs. Bond pads are also provided to allow wire bonding for the electrical connection. And the major characteristics is DC bias can be supplied here and the output signal can be taken out by these wire bondings and bond pads. However, there is another alternative technology recently have created research at Princeton that is called flip chip method that can reduce series of inductor and shunt capacitance. This is all about the passive device for the MMIC technology. In this slide, we will give you an overview about the types of MMIC and some application area. So in terms of types of MMIC, we can use and we can fabricate different kind of MMIC. For example, low noise amplifiers, power amplifiers, and limiters, switches, phase shifter, voltage control oscillators, and as well as mixture. So there are some application about the military, space, and civil area. So these kind of things are much more important in our technological society. So in the military case, we can use this MMIC technology for remote sensing and passive MMW imaging, instrumentation, electronic warfare, and smart monitoring and decoys, this kind of things. And in the space area, we can use this MMIC technology for satellite communication, radio emitters, astronomical fields, synthetic aperture radar, and so on. In the civil area, this technology is much more important for the satellite TV receiver, wireless communication, and so on, fiber optical system, LAN, GPS, Bluetooth and high-speed internet, RFID system, and medical system, and so on. This is all about my introduction of MMIC technology, chapter 1. If you have any question, then you can ask me in the comment box. I will try to give you the proper answer against your question. So thank you for your watching this video.